Then, if you look at the elevation, change of the elevations along the water depths, then you can again compare with Green's law. Then, as you can see, the measured 3 points, they are slightly smaller than the Green's law. However, if you look at the measured wave height, the random height near the Kamaishi Bay, say that's Kamaishi, that was about 15 meters, and this corresponds, reasonably corresponds to Green's law. And then, from the information of the time series of your sinusoidal fluctuations, we can estimate the spatial distribution by multiplied by the phase velocity, then both the sinusoidal fluctuations, and as you can see, as the wave propagates, the tsunami propagates in the shallower area, this steeper portion of the crest is getting narrower and narrower. This means that because you are getting into the shallower water depths, therefore your wavelength is getting shorter and shorter, because again the wave phase velocity c is again proportional to square root of h. Okay. Then in the shallower water, because the square root of gh is based on the linear wave theory, but in shallower water, as your wave height is getting higher, then the non-linearity of the wave, the tsunami, can act as to influence on the tsunami behavior. And then in one of the simple nonlinear wave model, the phase velocity is now proportional to square root of h plus eta. So now the phase velocity is a function of the size of the fluctuation itself. Therefore, if you have higher elevations, then this person tends to propagate a little faster than the others. So up to now, we just talked about the one-dimensional phenomena, deformation of tsunami, but in reality, we should have a two-dimensional horizontal change. And due to the variation of the 2DH geometry, we should have different deformation phenomena of tsunami. That would be refraction or diffraction or reflection. So the refraction, maybe most of you may be familiar with the refraction phenomena, but if your water depth change, again, your phase velocity does change. And in order to match your wave phase conditions, the crest lines, then each wave were forced to change its propagating directions. And this direction change is again expressed by, simply expressed by the phase velocity under the assumption of your parallel contour line. Then that is the sort of well-known Snell's law. And as you can see, wave direction sine theta is proportional to the phase velocity c. Okay? And especially in case of shallow water, again, your phase velocity is square root of gh, and square root of gh is something like this. Therefore, in shallower area, your phase velocity c changes abruptly. Okay? Therefore, this kind of diffraction phenomena can be dominantly observed in a shallower area, or in case of like long wave tsunami. And not only diffraction, we also have diffraction phenomena. And diffraction phenomena, if you just look at the transformation of the wave energy, then we can really explain. However, for example, if you have some breakwater or something like this, then in reality, some of the wave energy is actually leaked behind the breakwater, and you have some wave energy even behind the breakwater. And this kind of features can also be analytically estimated in case of the very simplified case. However, the one thing that I'd like to focus on here is that we are looking at tsunami, and as you can see, this is the horizontal scale. Horizontal axis is expressed by x divided by L, and this L is wavelength. Therefore, especially in case of tsunami, we are looking at very small values of this horizontal scale. Therefore, especially in case of tsunami, we are looking at the area that is close to the origin. Therefore, these numbers show the wave height, the ratio of the wave height. Therefore, usually behind the breakwater, you tend to have very small wave height, as you can see here. However, in case of tsunami, because your wavelength is very long, therefore your wavelength is relatively, wave height is relatively high. Then I'd like to show some example of measured inundation, the tsunami height that we have already obtained through the field survey. And as you can see, this is the Yori Bay, and due to the refraction phenomena, we observe a very, very high inundation height at near the top tip of this peninsula, and this height is very large, nearly 40 meters compared to the other places. And if you look at the contour lines, this is the 50-meter contour line, and this is 100-meter contour line, the water depth. And as you can see, this kind of the convex profile of your contour line, this can force the wave to diffract. Therefore, some of the wave may be concentrated around this area. So this may be the reason why we have a very large inundation height here. And then, similarly, we have again we can apply the Green's law, and then Green's law is basically a conservation of your energy flux. And then, in this case, if you have a bay, your horizontal width of your bay is getting narrower and narrower. And then, because you have the same energy flux here, therefore your waterway getting narrower, then your energy tends to be more concentrated. Therefore, this B, the width B, does also affect on the amplification of your wave height. Therefore, roughly speaking, as you go inside, then you will observe that you will have a relatively larger, higher tsunami inundation height. Then, related to the diffraction, we have some other interesting phenomena. This is the case of the Indian Ocean tsunami in Sri Lanka. And then, as you can see, this gray zone is the land of Sri Lanka. And then Sri Lanka was actually surrounded by the continental shelf. Here the water depth is relatively shallower, and then the other places are much deeper. Therefore, due to this sudden change of the water depth, some of the wave may be deflected, then some of the wave may be diffracted. Then, so this is diffraction. So here the top is the deeper and bottom is shallower. Then due to the change of your phase velocity, wave starts to diffract. However, the wave diffraction can also occur if the wave is deflected. Then if you propagate from the shallower area to deeper area, you have the same path of your wave diffraction. However, if your wave angle is like this, a little smaller, then this may be reflected again because we have no way to go outside of this continental shelf because of the very shallow angle of your east. So, in this case, some of the waves are actually deflected at the edge of the continental shelf, then the waves are start to trapped. Then we can compute the inundation phenomena. And we have, especially in case of the Tsunami coast, we have bay, and bay has some resonance conditions. And this is also related to some tsunami deflections. And due to tsunami deflection, some of the wave, and especially the tsunami period and the resonance period of the wave matches with each other, then the amplification can also be observed. Then finally, I'd like to show about the deflection, another deflection phenomena of tsunami. And one of the effective way to reduce the wave height, tsunami wave height, may be some structure that is developed in relatively deep water, because so this is one example of the tsunami breakwater that was developed, constructed in the water depth of 6 meters, very deep. Then we developed this structure by using the cases. Then the point here is, even though the tsunami height is very large, however, your water depth is deeper here. Therefore, most of the part of your water column is still covered by this structure. And then this kind of structure can reflect the tsunami to the outside of the bay. Then, so some computation actually reveals that this is very useful, and this is effective to reduce the tsunami height inside the bay. However, this is just a computation. Therefore, we did some field survey to look at the actual tsunami inundation height, both inside and outside of the breakwater. Then this is the result. This is Kamaishi Bay, and this is where we have a tsunami breakwater. And as you can see, the inside, the tsunami inundation height was relatively smaller. And then it's very interesting to see that just outside of the tsunami breakwater, we tend to have a very high tsunami inundation. So this high inundation height may be partially due to the reflected wave at the tsunami breakwater. And then plus, if you look at the bay, Yoshimitsu Bay, that is just next to the Kamaishi Bay, then tsunami inundation height is very large. And then it's time to switch to Sato sensei. But I mainly talked about the tsunami propagation, deformation in the seawater. However, if you look at the deformation very close to the coast, we have very different phenomena, and we have many other features that can deform the tsunami waves, and that can make some of the local concentrations of tsunami external forces that can enhance the damage of the structure. Okay, so sorry for I'm spending some time, but let's switch to some.